projects. In this video, we are going to explain about a project titled Melanoma Detection Using an Objective System Based on Multiple Connected Neural Networks. So now coming to the introduction part. The introduction and data-driven approach hold immense promise in the field of dermatology, as it not only aids in early and precise melanoma detection but also helps reduce the potential for misdiagnosis, unnecessary biopsies, and treatment delays. As the system evolves through further research and development, it has the potential to revolutionize melanoma screening and improve the overall efficiency and accessibility of skin cancer diagnosis, leading to better patient outcomes and saving lives. By leveraging deep learning techniques, the system can learn from vast amounts of annotated data, continuously refining its performance and improving its ability to accurately identify melanoma. So now coming to the objective part for this project is to harness the power of artificial intelligence and deep learning to create a highly accurate and efficient diagnostic tool for melanoma detection. By combining advanced neural network architectures with vast datasets, the system aims to revolutionize skin cancer diagnosis, contributing to earlier detection, improved patient care, and ultimately a positive impact on public health. Through the power of deep learning, the system can continuously learn from a vast and diverse dataset of annotated images, refining its performance over time. This iterative learning process enables the system to adapt and improve its detection capabilities, ultimately increasing its sensitivity and specificity in identifying melanoma lesions. So now coming to the requirements part, we have two types of requirements, that are hardware requirements and software requirement. In hardware requirement, operating system as Windows is required, processor i5 and above, minimum 4 GB of RAM is required, hard disk 20 GB and above. Coming to the software requirement, Python IDEL, that is 3.7 version is required. So now coming to the methodology part, first upload dataset. The process begins with uploading a dataset containing dermoscopic images of skin lesions. This dataset is a collection of images from various sources which serve as the input for the subsequent step of the skin cancer prediction system. Second, pre-process dataset. After the dataset is uploaded, it undergoes a pre-processing phase. Pre-processing involves various steps such as image resizing, normalization, and noise reduction to ensure the dataset is clean, consistent, and suitable for further analysis. Third, run subjective 5 classifier. The system utilizes a subjective 5 classifier to categorize the pre-processed dermoscopic images into 5 different classes based on visual features. This classifier is manually designed and its performance relies on human expertise in distinguishing lesions from malignant ones and identifying different types of skin cancer diseases. Fourth, run objective algorithm. In contrast to the subjective classifier, an objective algorithm based on machine learning or deep learning techniques is deployed. This objective algorithm uses the pre-processed dataset to automatically learn and recognize patterns in features indicative of skin cancer. By relying on data-driven insights, it aims to achieve more consistent and reliable predictions compared to the subjective classifier. Fifth, run ISIP PH2 combined objective algorithm. To further enhance the prediction accuracy, the system incorporates a combination of objective algorithms such as ISIP, which stands for International Skin Imaging Collaboration, and PH2 stands for Personal Handheld Dermatoscope datasets. These datasets contain a diverse range of skin lesion images, enabling the objective algorithm to be more robust and effective in identifying different types of skin cancer. Sixth, run extension broad learning. As part of continuous improvement, the system explores extension techniques like broad learning. Broad learning involves a high-capacity learning model capable of capturing complex features, which can further boost the predictive performance of the skin cancer detection systems. Seventh, run extension IRF with objective CNN. Another extension technique applied is integrated receptive field, which stands for IRF with objective convolutional neural network, that is CNN. IRF enhances the neural network's receptive field, enabling it to process larger image patches effectively, leading to improved feature extraction and classification accuracy. 8. Accuracy comparison graph. To evaluate the performance of the various algorithms and extensions, the system generates an accuracy comparison graph. This graph visually represents the accuracy achieved by each method, enabling a comparative analysis to identify the most effective approach. 9th, performance comparison. Apart from the accuracy comparison graph, the system also compares the performance of different algorithms based on metrics such as sensitivity, specificity, precision, and F1 score. This comparison allows for a comprehensive assessment of the strengths and weaknesses of each method in detecting skin cancer. 10th, propose versus extension execution time. In addition to accuracy and performance, the system also measures and compares the execution time between the proposed algorithm and the extensions. This analysis helps identify the trade-off between accuracy and computational efficiency, crucial for real-world deployment. 11th, skin cancer prediction from test image. Finally, the system puts the prediction model to the test by using a test image not previously seen in the training dataset. It processes the test image through the most accurate and efficient algorithm, generating a prediction indicating whether the skin lesion is benign or malignant. So now coming to the execution part. To execute the project, first we need to open the code folder. So here we have a folder named as PyCatch. In this we are containing a Python file which is containing the Python script in it. Another folder named as GAN segmentation. In this folder we are containing some images over here. Another folder ISIC dataset. In this we are containing some images over here. And another folder iterative random forest. In this folder we are containing some dataset over here. Another folder named as model. In this we are containing some .npy files and .h5 files which contain the deep learning algorithms information. These .h5 files can be loaded into the project code during runtime to utilize the trained model for various tasks such as making predictions on new data or performing specific operations. Another folder named as ph2 dataset. In this we are containing some images over here, and another folder named as ph2 GAN. So in this we are also containing some images over here. Another folder named as ph2 model. In this we are containing again same that as .npy files and .h5 files which contain the deep learning algorithms information, and these .h5 files can be loaded into the project code during runtime to utilize the trained model for various tasks such as making predictions on new data, performing specific operations as I have told you earlier. And another folder named as test images. In this we are containing some images over here for testing. So now all these files are the Python files which are containing the Python script in it. And here this is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file to execute the project. Now to run the project, double click on run.bat file to execute the project. So here this is the graphical user interface. With this we are interacting with the program. So now click on upload dataset button to upload the dataset. Here I am selecting this dataset folder over here. And so now click on select folder over here. So now click on select folder over here, and you can see that the dataset has been loaded over here. And so now click on pre-process button to extract LPP, HOG and segmented path from images and then build train dataset. So here you can see on this screen that here we have 3 images over here. So we can see LBP, HOG and GAN segmentation extracted from all images and then showing one sample images with LPP, HOG and segmentation. So now closing these all images. Now click on run subjective 5 classifier button. And you can see over here that ISIC dataset total images found to be 900. So by clicking on run subjective 5 classifier button to train the images with 5 classifiers, and so you can see that we have got the output over here. So all algorithms are trained with that images, and for each algorithm we have calculated accuracy on test images. And now all 5 algorithms model are ready, and so now click on run objective algorithm button to calculate the accuracy. So now here on this screen with proposed algorithm we got 98.33% accuracy, and so by clicking on run ISIC PH2 combine objective algorithm button, now here on this screen you can see that combined ISIC and PH2 proposed accuracy is 99% and execution time is 22.45. So now click on Run Extension Broad Learning button and you can see that the accuracy for broad learning is 0.994 and for extension time is 0.84. So now click on Run Extension IRS with Objective CNN button. So here you can see the output. We can see proposed system got high accuracy and TN values. So now going back to the main application and closing this window. So now click on Accuracy Comparison Graph button to get the graph. So here you can see that in pink line refers to proposed system over here and has high accuracy from starting epoch, and in this graph x-axis represents epoches and y-axis represents accuracy. So now closing this graph. Now click on Performance Comparison button to get the graph. So here in this graph x-axis represents algorithm names, that is with TP, FP, FN and TN in different colors, and here y-axis represents count of each matrix, and in this graph proposed system has high TP and TN values compared to other algorithms. And now click on Propose versus Extension Execution Time button. So you can similarly see that here we have the algorithm name and here the y-axis represents count of each matrix. So now click on Skin Cancer Prediction from Test Image. Here suppose if I am uploading this 6th image, so now click on Open button over here. Here in this image you can see that image predicted as malignant. You can test with another images also. Just click on Skin Cancer Prediction from Test Image. So now here you can see that here I am selecting this 4th image and now click on Open button to get the image. So here you can see that in blue color text you can see image predicted as benign. So now closing this image and coming back to the conclusion part. Overall, melanoma detection using an objective system based on multiple connected neural networks holds great promise in the fight against melanoma and skin cancer. With its potential to significantly impact early detection and patient outcomes, this innovative technology stands as a testament to the transformative potential of artificial intelligence in healthcare. As the system continues to evolve and gain acceptance, it has the capacity to become an invaluable tool in the battle against skin cancer, saving lives and improving the quality of care for patients worldwide. As a result, patients with melanoma can receive prompt medical attention, potentially increasing their chances of survival and reducing the need for more invasive procedures later in the disease progression. Moreover, the objective nature of the system reduces the subjectivity often associated with visual diagnosis, mitigating the risk of misdiagnosis and unnecessary treatment.
For updates on latest project videos, please visit True Project's YouTube channel and subscribe.